So if you agree, shall we go move on with a different approach?
Okay, sir.
Okay, good, great. So let's set up a few ground rules. The ground rules are same as the postulates or the points of the theory, right? What we are going to do is that we're going to talk about two elements who have been covalently bonded. The entire thing would be discussed by the number of pairs of electrons around the central atom, not each atom, the central atom, of course, and whether these pairs are lone pairs or bond pairs will that matter, right? So the valence shell electrons would be of the main outer shell. They can repel each other because they have the same charge. A lone pair of electrons will repel more than a bonded pair of electrons. So how are we going to treat it? We do understand this specific formula. Lone pair repulsion is the maximum, and bond pair repulsion is the minimum. However, lone pair bond pair repulsion can be put right in between. All right. When there will be repulsions between multiple and single bonds, we'll treat them as same for repulsions between single bonds. But remember, the double bond repulsions would, the repulsions between the pairs of double bonds would be greater. So we are trying to go with a shape that is more stable, and we are going to keep the shape by making sure that the forces of repulsion are kept at a minimum. याद रखें forces of repulsion किस तरह से minimum रहेंगी? If we keep the electron pairs as much apart as we can. जितना electron pairs को एक दूसरे से दूर रखेंगे, उतने ही हमारे पास forces of repulsion minimum रहेंगी. जितनी forces of repulsion minimum होंगी, उतना हमारे पास stable structure होगा और वही उसकी actual shape होगी. Fair enough. These were the few ground rules. We have already studied the rules, so I just went through that. Are we good?
Yes, sir.
Okay. So what I'm going to do is that I'm going to stop sharing the book. I'm going to open up a whiteboard. And we're going to work on it with the help of whiteboard. Of course, all of you have the option to annotate. So we'll go according to that. This is the AS whiteboard. We have been working on the whiteboard before you came, Ali. So that's why you can see the whiteboard filled up. But I'm going to move to a cleaner page. Okay, let's go on with a clean page. All right. Okay. Now, before I start asking you questions, I'm going to assume two things. I'm going to assume that A is every time going to be the central atom. And B is every time going to be the surrounding atom.
Sir, are you drawing something?
Can't you see the screen?
No, sir.
Just a second. Let me save it. It would be easier for you to see. How about now? Can you see it now?
Sir, I can see the previous page.
Okay, let me restart it. I guess we were having the same problem last time, so I guess I need to. I guess now you can see this page, right?
Sir, I can see the table.
Can you see the page change I'm doing right now?
No, sir.
What about you, Ali?
No, it's on the page subshells orbital, that page.
Yes, it's the table.
Just a second, let me see what I can do. So to begin with, let's take the first example.
Are you drawing anything right now?
Can you see what I'm writing?
No.
Right? Can you see what I'm drawing right now? Okay, if I put them at 90 degree, like this, this, and this, let me tell you, these two are 180 degree apart, right? And these two are 90 degree apart, which means they are not placed with a appropriate order. This won't be a right option. Let's think of a correct
We
one.
can try 120.
120, that would be a great idea. See, if I go with 120 like three corners of a triangle, then they would exactly be 120 degrees apart, like an isosceles triangle, like this one, right? And all of them would be equally apart from one another. Are we good? Okay,
Yes, sir.
let's get back to page number 4. I'm going to give you a few examples. If I talk about example number 2 and I write a chemical example for it, you would easily understand what I'm talking about, right?
Yes.
I'm only writing BCl2 since any other example I write with group 2 elements would be an ionic example. This is somewhat as closer to covalent example as I can, with beryllium being the central atom and both of the chlorines are surrounding it. Any other example, magnesium chloride, calcium chloride, would be more of an ionic example than they are covalent, since those are pretty good metals. Beryllium is not as good as a metal as magnesium or calcium or other ones in group 2 are. Okay, so I think with this kind of example, as soon as you see the example, you would quickly understand that what I'm trying to hint over here is that this beryllium automatically becomes A, or the central atom. This B automatically, Cl becomes B, or the surrounding atoms, which means you can put A right in between with B surrounding it at two corners with 180-degree angle, and you would understand what the examiner is trying to hint you with the formula. So as soon as you see the formula, actually you can come up with a proper displayed formula, and from there on onwards, you can work your angle or you may work your shape. Make sense?
Yes, sir.
Okay, let's do the same. In order to make more sense to it, let's do the same with example number 3. Okay, let me quote a couple of examples. BF3, BCl3, AlCl3. Most of these examples would be, if they have a covalent character, would be something like this. Now, you're already sure about the angle. Let me tell you, it has a triangular shape. Right?
Yes, sir.
Since there are 3 corners of a triangle. Now you know the angle, now you know the shape, now you know more examples to this setting. From there on onward, scientists work their way with other particles as well. And if I talk about example number 4, of course, I'm going to extend it a little bit more. We have 1A and we have 4 Bs. If I have to stick with two-dimensional structure, of course, I would always be coming up with this kind of structure, right? Which we previously did back in IGCSE. all of them at a 90-degree angle. Since a circle is composed of 490-degree angles, so yeah, we can put one of the B's on top, one at bottom, one at right, one at left. So that would tell us what the whole structure is about, right? But this is for a two-dimensional structure. The bad news is for all of these kinds with 1A and 4Bs, all are three-dimensional structures. So this arrangement won't work for us. Even in case of some example number 3, we have some 3D models, which I will come up with when it comes to the book examples given in the book. Of course, as soon as we get back to the book, I'll clear those examples out. The point I'm trying to make is that don't just look at it in terms of atoms placed randomly. Scientists have worked their way out and they call all of this with one word, symmetry. Whoever had made this universe, and I believe Allah made the universe, it's one of my beliefs, the most strongest one at that, and he is actually a perfect creator. Even for the smallest of structures, there is so much symmetry in terms of angles and shapes that you can keep on studying them for life, right? I hope it makes much more sense now. That when he wanted to combine two atoms, when he wanted to combine three atoms, when he wanted to combine 4, 5, so on and so forth, every time he had some specific structure, some specific bond angle, some specific ideas of shape with him. And that's what we are studying right now. So I want you to get all creative, all mathematical whenever it comes to a structure. Think about the angle, think about the 3D shapes, and it would be really helpful if you take help from a YouTube video that is not about a teacher's lessons, that has actually used some 3D drawn structures to explain these structures to you. It would be a very good idea. Just write the name of the structure and write the word 3D in the YouTube search bar, and they'll explain it to you. Every structure has a separate video on YouTube. That's the best part about it. Are we good?
Yes, sir.
Is this effort a little bit helpful? Understanding the angles, the shapes, the structures?
Yes, sir.
Yes, sir.
Good, good. Now let's get back to the book. So I'm going to save it. And I'll share it with you later. And let's get back to the book. So when we were talking about AB4, I mean 4 B atoms and 1 A atom, central atom, methane, ammonia, and water examples came up. These examples were pretty good to understand about 4 lone pairs, how they are arranged if they're all bond pairs, how they are arranged if we have 1 lone pair and the rest 3 bond pairs, how they're arranged if we have 2 lone pairs and 2 bond pairs at the same time. So I guess now this makes more sense to you. This also proves the point of repulsions for us, that lone pair and lone pair repel themselves more than they do to bond pairs. Do I need to explain any of this again, or should we move on? What do you say?
Move on.
All right. Moving on. Let's go with more shapes. Boron trifluoride. Boron trifluoride is actually an electron deficient molecule. We have already studied that. The FBF bond is 120 degrees, and this is trigonal or triangular planar. We use both words, trigonal or triangular. And if the structure can be drawn in a 2D shape, remember, we're going to use the word planar. Planar means the structure can be drawn on a plane, and it means it can be explained in 2 dimensions easily. Though the structure had a 3rd dimension shown, but planar means that can be drawn easily. Right? Moving on. Carbon dioxide. Carbon dioxide has 2 carbon-oxygen double bonds. Now, on both the sides, we can see the double bonds. And there are no lone pairs on the central atom. There are no lone pairs on carbon, right? Keep that in mind. He's not talking about oxygen. There are 2 lone pairs on this oxygen. There are 2 lone pairs on this oxygen. So he's not talking about oxygen. He's talking about the central atom. Keep this line in mind. It's better to write on the book so that this doesn't confuse you when you read it when you're revising. The 4 electrons in each double bond repel other electrons in the similar way to 2 electrons in a single bond. This is what the confusing postulate meant. These 2 double bonds, this double bond has a set of dot cross electrons, actually 2 sets. This double bond has also a set of dot cross electrons, 4 electrons, 4 electrons. These 4 electrons repel themselves almost in the way the single bonds do. What he's trying to say, if there was a double bond and there was a single bond, the double bond would have repelled the single bond more. But since there are 2 double bonds, the repulsion from both sides would be equal. And we can consider them as single bonds. I mean, we can talk about the repulsion pretty similar as would have been with a single bond. Although the strength of the double bond repulsion is more than the single bond, but when there are 2 double bonds, we can consider them in the same way. I hope that makes sense. Does it?
Yes, sir.
Since the structure is in a straight line, using the word straight line is somewhat childish. We use the word linear for this structure. And the angle is 180 degrees, as explained earlier. I hope this example comes easy to you since we have discussed an example like this before. The only difference is that I was talking about single bonds. This example consists of both double bonds. Hence the postulate acting similarly. Moving on, phosphorus pentafluoride. This is somewhat different. Phosphorus pentafluoride has 5 bonding pairs. We call it an expanded octet. The repulsion between the electron pair results in the most stable structure being one where 2 pyramids with bases of 3 angles are joined. We call this structure trigonal bipyramidal. I hope you understand that a pyramid is something like this. And we're talking about the actual pyramids of Egypt, which actually gives an imagination for a better structure. Trigonal bipyramidal means there are 2 pyramids with bases of 3 angles. 3 of the fluorine atoms lie in the same plane as the fluorine atom. This one, and this one lie in the same plane. The FPF angle is 120 degrees in between these. He has also already considered it. 2 of the fluorine atoms lie above and below, and these are at a 90-degree angle to the ones, to the other 3 ones, of course. So there are 2 angles that you need to remember. All right? Make sense? Maybe the whole writing thing is making it difficult for you to see. So there we have the 120 angle, and there we have the 90 angle. Are we good? Can we move on?
Yes, sir.
Remember, in case of this example, there is one structure or shape name, but there are 2 angles to be mentioned before you get complete marks for it. In all previous examples, what you had to do is to write one name of shape like this and one angle. Let me take you a little back more. One name of shape and one angle, right? But in this example, starting from phosphorus pentafluoride, there would be one name, but there would be two angles. Okay, so moving on, another example like this, sulfur hexafluoride, another expanded octet, all bonding pairs, no lone pairs. The equal repulsion between electron pairs again results in a very stable structure. All FSF bond angles are 90 degrees. The shape is octahedral, means 8 heads. Octa means 8, hedral means heads or sides. So 2 of them are in the plane, 2 of them are reaching out to us, 2 of them are going away from us. All balanced angles, hence all of them are 90 degrees to one another. So one shape and one set of angles. Make sure you are able to come up with the name of the shape, the angles, the bonds for which the angles are concerned, the dot cross formula, as well as, if not the ones drawn in brown, the ones drawn in black shape. Means you are able to draw this. Like this, right? You should be able to do it like this. I hope that clears out what you should be able to do in exams. Any questions so far?
No, sir.
Okay, let's go with these questions as a practice, and we can do them orally. Question number 7, part A. Laiba, let's start with you.
Draw a dot and cross diagram for
Mhm.
a molecule of selenium hexafluoride. A single selenium atom has 6 electrons in its outer shell.
Okay, my question to you is, can you predict the shape, which is actually part B of this? You can turn your pages over of the book, and you can tell me from the book. You don't have to do that orally. Do you have a hard copy of the book in front of you right now?
Yes, sir.
Good. You can turn on over the pages. You can go to the previous or this page and try finding out a similar structure so that you can answer the question. I won't ask you to draw the dot and cross diagram. Let's come to part B, predict the shape. Remember, the shape is always predicted in 1 or 2 words. That's about it.
Octahedral.
Octahedral, good. How were you able to predict its shape as octahedral? Which structure was similar to this one?
Sulfur hexafluoride.
Easy. Now, this part of the name or the structure would strike or ring a bell first thing in a question. Are we good?
Yes, sir.
Okay. Next question is about a drawing. Let's not go with that. But let me ask you, Ali, in case of part C, do you know the name of the structure for phosphorus 5 chloride? Once again, you can look it on the book. That's fine by me. It's not cheating. It's going through the stuff, jogging your memory. And these exercises are always helpful. I don't call that cheating.
All right. Trigonal bipyramid.
Right. There are 2 sets of angles in that one. Can you tell me the angles as well?
120 and 90.
Good, good. Can you imagine what trigonal bipyramidal looks like?
Yes.
Yeah, they are like 2 pyramids with the same base pointed towards 2 different directions. That's why bipyramidal. Bi means 2. The word bi means 2. Okay, moving on. Question number 8. In trimethylamine CH3 in Three CH3 groups are attached to nitrogen by CN bonds. The repulsion of CH3 groups is slightly greater than the repulsion of H atoms in ammonia. Which one of these bond angles for CNC bond in trimethylamine is correct? This question is for both of you. You may need to look at the structure and the angles in ammonia, go a couple of pages back, because the structures we started off with were methane, ammonia, and water. So you won't find the structure on the same page, of course. Try comparing it with ammonia. Now, ammonia has H atoms. This one has CH3. Let me draw the structure for you for your ease. It's going to be something like this. For CH3, I may have written CH3 directly, but I'm trying to draw an open structure for a better imagination. I would draw the other one too. And then there is lone pair on top. You may draw it like this. CH3, CH3, CH3. Now, my drawing has nothing to do with these angles. Remember, it's just to give you an idea. If I have drawn it in any other way, of course, that would have given you the idea which one of these angles would be correct. So before I ask you the answer to this question, can any one of you tell me the actual bond angle in ammonia? Okay, let's give you separate tasks. Laiba, go to the end of the book where there are all the answers for the topics in the book. Try finding chapter number 4, question number 8, and the answer to this one along with the reason. Ali, go back up a couple of pages, find the structure of ammonia, and tell me the angle given about it.
Yeah, I know the one angle of ammonia.
Yeah, and that is
107.
107. Now, the angle for methane is?
Sir, there are no.
You sure?
Yes,
I
I think
think
so.
I think the answers are in between the glossary and the appendices. Not the exact
Okay,
end of the book, but a little before that. Try finding the answers. You will find those answers. Maybe they're even before the appendices and the glossary. Try going back and forth on the pages a little bit. I hope you will be able to find the answers. Okay. Yes, Ali, getting back to you. What's the angle
Yes,
for
what is it?
methane?
109.5.
What's the explanation given about why the angle reduces from 109.5 to 107 degrees? There are a few words or lines written, and they
The lone
explain
pair and the bond pair repulsion is
repulsion.
greater.
Right.
Yeah.
Great. There are no lone pairs in methane, so all the angles are 109.5. But since we have introduced the lone pair in ammonia, and the lone pair bond pair repulsions are greater than bond pair repulsions, so the repulsions force the angle in H and H to be reduced to 107 degrees. And I explained, I asked you both to write that the angle would be greater than 109.5 in case of the lone pair nitrogen-hydrogen angle. Do you understand this reasoning? I mean, do both of you understand this reasoning?
Yes, sir.
yes, sir.
Good. Laiba, were you able to find answers?
No, sir.
Really? I have them at this book. Just give me a minute. So we have this Appendix 3, Appendix 2, 1, periodic table. Then there are a few rules about the chapters. Wait a minute, have I told you? I might have told you the wrong page to look. Just a minute, let me see. Yeah, now I'm guessing I've told you the wrong place to look. So you don't have to be exact. Now, let's talk about your guesses. Ali, your guess first.
Just a minute, sir. We have to tell the CNC angle, the straight line one, or the which one exactly?
CNC means this angle, like this one. This one is 107. What about this one?
Uh-huh. Oh,
Okay, let me use a different color. What about this one? Since this one is 107 over here.
maybe D about 120. Greater
Uh-huh.
than 109.1. Yeah.
Okay, that's your choice. What about you, Lava?
C.
Okay, let me tell you, this one is closer. Okay, 120 is the angle which is when there are 3 pairs around the central atom. Since there are 4 pairs around the central atom, 1, 2, 3, 4. So either it's about this one or it's about this one. Since 4 pairs are never 3D, so this won't be right. This may happen in more than 4 pairs, but not at least in 4. And this is for 3 pairs. This one is for 3 pairs, right? Okay,
Yes, sir.
good, good. Now, I am going to do one. This is a Pakistani stream book. Many of other books from Pakistani or Indian or American streams may contain the same thing. So you can pick any of those reference books for this idea. This goes on with Valence shell electron pair repulsion theory and a basic assumption, a few postulates that we have already discussed. Why am I picking this book? Because this book gives you a very good idea with AB, AB1, AB2, AB3, AB4, since this huge table has already been taken from another English book. So this pretty much would give you the idea what the shape would be, how many total pairs are those, whether those pairs are bonding pairs or lone pairs, and what can be the possible examples for the molecules regarding those shapes. What can be the possible angles, right? You might see bent or angular words for these angles. You will also see the same words in many marking schemes with different examples. This also goes on with explanation. For molecules containing electron pairs AB2 type, BeCl2 or MgCl2, AB3 with no lone pairs such as ALH3, BF3, AlCl3 trigonal planar, like this one. They also discuss a certain type that has been used in past papers, and I specifically use this book because I've seen this exact same example in past papers. All right. Then they ask the A-level students to come up with an appropriate answer, be it MCQs or theory questions. Now, when they pick an example like this, you already see there is tin, SN, as an example. It has a lone pair up top, and then there are single bonds of 2 chlorine atoms on each side. And then it tells you that this one, or this angle, whatever that is, this angle is less than 120 degree. Can any one of you explain why this angle is less than 120 degree? Come on, let's try. Remember the repulsion rule? Can you explain it on the basis of repulsion rule? One of the postulates that we have studied. Come on, let's try. You learn by making mistakes. Why do you think this angle is less than 120 degree? Since there are a total of 3 pairs, every angle was supposed to be 120 degree. But of course, one of the angles is less than 120 degree. There has to be an explanation. I don't know which exact paper quoted this example, but this example exists in past 5 to 8 year papers in A levels. Anyone?
Lone pair.
Right, both of you are correct actually. The lone pair over here exerts more repulsive forces on both of these bonds, making this angle less than 120 degree. Now, I would like any of you to tell me what would this angle be? Or what would this angle be? Anyone?
Greater than 120.
Perfect answer. Greater than 120. That's about it. That's what you are supposed to write in exams as well. Do not quote a value. Do not say 120.5. Do not say 121, 122. Do not say anything like this. Greater than 120. That's about it. Good enough? Let's move on to another example. Let me tell you, this kind of example won't come as a part of A levels. If it does, the question would be about something else and not comparison of a double bond with a lone pair. I've never seen questions with double bond with lone pairs where they ask for reasoning about it. So let's forget this example. However, this has been an example in A levels. I specifically picked this book because this book has many examples from past papers. And if you read these lines, it would tell you what the shape is. My question to both of you, why is the shape perfectly triangular? Or you may also use the term trigonal. Why is the shape perfectly triangular or trigonal?
Bond angles are 120.
Why? You're right with your reasoning, but this is another set of justification in which you're not actually answering as a part of reasoning for the question. You're running around the question by justifying with another set of reasoning. So why are the angles exactly 120? Every time try to come up with a reasoning that explains the distance between the bonds, or that explains the repulsion between the bonds or bond types, something like that. That would be a perfect reasoning. Like in the previous question, you came up with an answer that explained the repulsions. Try doing the same with this one. Come on.
Well, there are three bond pairs, and all of them will exert the same repulsion on each other.
Perfect. That would have been an answer I wanted. You can say there are three bond pairs and all of them actually repel them with equal forces. You can say there are three bond pairs and the bond pairs are double bonds, or they have four electrons and four electrons exert equal forces on the rest of the four electron based bond pairs. Whatever you'd like to say in terms of bond pairs, double bonds, four electrons, but them exerting an equal amount of force on all sides would be a perfectly good answer. After quoting about the bond pairs or the repulsions or the type of bond or the number of electrons, then you can go on ahead and talk about 120 degree and your answer would be fine. But just giving the answer that they are 120 degree each will not justify it. You won't get marks. I hope both of you get the point I'm trying to make here. Do you?
Yes, sir.
Yes, sir.
Great, great. Moving on. Next example is of methane. I guess we have explained it a lot already. Apart from methane, the good part about this book is that it gives you all possible angles, many more than what's quoted in your actual book. All right. So if the A-level examiner comes up with a similar example, but different formula, like instead of methane, he comes with tetrasilane or with germanium, four hydrogens with germanium, anything like that, you would always be able to come up with an answer. All right. Next up is methane. Why the angle is 107.5, the lone pair and the bond pair repulsions are all explained over here. Moving on, they also explain the structure of methane, or they discuss the structure of water in this case. All right, water in this case, and why it's reduced to 104.5 because of two bonds. Other examples such as water are also given over here. So it would be very easier for you to go with more examples or any kind of examples, similar examples that the examiner can come up with. All right. Okay,
Yes.
let's work in another way. Remember, we had a name of a structure that was trigonal bipyramidal, right? And the example in the book was PCl5. Can you come up with a similar compound by not changing phosphorus and replacing the halogen with any other halogen you like? So another example for the same structure would be, come on, think
EFR.
about it. Perfect. Ali, your turn.
Phosphorus pentabromide.
Right. So you already know what kind of examples you can come up with to discuss about the similar structure or similar angles, right? So this
Yes.
today's lesson gives you a very good idea of how things work in whisper theory, how they can come up with different examples to ask the similar question. All right. And every time when we talk about whisper theory, what you need to put into it is what kind of shape it can have, what are the angles for it, and why those angles or those shapes are justified by the repulsive forces between the electron pairs on the central atom, be those pairs are bond pairs or lone pairs or whatever. Make sense?
Yes, sir.
If this makes complete sense, let me tell you, we are done with whisper theory. That's about it.